Okay, can you see the screen?
Yes.
Yes, sir.
Yes,
Yes,
sir.
sir.
Sir, you are muted.
Okay, can you hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. If F and G are 1, 1, then G composite F is 1, 1. Correct? This we discussed last time. And here F composite G doesn't make sense. Does F composite G make sense in this case? Do you understand the question? Does F composite G make sense? Yes. What is the meaning of F composite G? That means first we apply G and then F. But that doesn't make sense because the range of codomain of G is Z. And if you want to apply F after G, then domain of F must contain range codomain of G. Here G composite F makes sense means we are first applying F and then G, because G composite F of X is G applied on Fx. So first F and then apply G, and therefore to apply G, F of X, if X is in domain of F, then F of X is in domain of G, and then we can apply G. G composite F makes sense, but F composite doesn't make sense, right? Do you understand what I am saying? Yes.
Yes, sir.
Okay. Now further, if F and G are onto, then what we saw, the composite function is onto, right? If combination of these two statements, if F, G are bijections, then what can we say about composition?
Composition also
Bijective, right? This is what we discussed last time. Then second thing we discuss, what is the converse? Converse of statements. So suppose f is a function from x to y, g is a function from y to z, right? If g composite f is or injective, then what can we say about f and g? What can we say about f and g?
F is on.
Then f is 1, 1, right? So x, y, and z, and this is g, this is f, and then g composite f. So if composition is 1, 1, then f is 1, 1. If this is 1, 1, G may not be. G may not be 1 1. G may be, may not be. Sometimes it is, sometimes not. But not necessary that G is 1 1. But certainly, if composition is 1 1, but then F is 1 1 or injective. So can you give example? Can you produce example of such functions? So find functions F from A to B, G from B to C, such that G composite F from A to C is 1 1, but G is not 1 1. And here F has to be 1 1, no choice. If composition is 1 1, F has to be 1 1, no alternative choice, but G may not be. So can you produce such example? Here I will consider simple set, right? So A, B, C, D. 4, 1, 2, 3, 4, 5. 5 element set, for example. This is B. We'll consider another set C. Is what I should take here, P, Q, R, S, for example. Now, if my function F is this, right? Then function G is this, 3 goes to this, 4 goes to, and 5 also goes to S. So this is F, this is G. Can you see the functions clearly? What is f of a is equal to 1, f of b is equal to 2, f of c is equal to 3, f of d is equal to 4. Is f function from a to b? Is f function from a to b?
Yes. Yes, sir.
G of 1 is equal to p, g of 2 is equal to q, g of 3 is equal to r, g of 4 is equal to s, and g of 5 is also s. Right, so both are functions. Now is f11, is f11?
Yes.
Yes, is
Yes.
okay. Is g11?
No.
No,
No.
because 4 and 5 are two distinct elements in domain of G, but their image is same, which is S, so G is not 1 1. What is G composite F? G composite F is from A to C. And what is G composite F of A? What are the images of, what is image of composite F, image of A under G composite F? What
P.
is it?
P.
G of F A, but F of A is P, and G of P, F of A is 1, right? And G of 1 is P.
P.
Correct. Correct. What is G composite F of B? Is G of FB.
Q.
But what is FB? FB is 2,
2.
right? So therefore, and what is G of 2? Q.
Q.
What is G composite F of C? Is G of C,
R.
and is 3 is R. What is G composite F of D? So G of FD, which is G of, what is FD? FD is 4. What is G4 is?
S. S.
So now composite F is completely determined. Is it 1 1? Is G composite F 1 1?
Yes.
Yes, sir.
Yes, sir.
Yes, right. And therefore, example where we see that key G composite F is 1 1, then F has no choice, but G is not 1 1, right? So now you find example. What is exercise? He give an example. Okay, we'll see this later on. What is second point we discuss in this? If G composite F is onto or surjective, then what? So we have proved this last time, right? Yes
Then
or
G
no?
is on.
Okay, second part it remains to prove. We proved first part, I think, right?
Yes, sir.
Right. So if G composite F is onto, then G is on. So F may not be. And in same example, in previous example, in this case, is G onto? Is G onto?
Yes.
Is
Yes, sir.
and is composite function onto
Yes, sir.
from A to C? But F is not onto. In previous, F may not be, maybe. So let us see the proof of this, which we could not complete last time. Okay, so what is given? What is our function? F is from A x to y, G is from y to z. G composite F from x to z is onto. This is our assumption. What is our claim? What is our claim?
G is onto.
G is onto. This is our claim. Okay, so consider this figure and Z, F, and here is G. Now we want to prove that G is onto. So how to prove, how to start the process? What do you want to prove? That is to prove. We want to prove that G is onto means what? What we want to prove? What we need to prove here?
For each Z in Z, there exists X in X, such that G of X is equal to Z.
No. What is domain of G?
Y.
I. So G is onto means for every element in Z, there is pre-image in Y under G. Correct? So what we need to prove? For each Z in Z, there exists Y in Y such that GY is equal to Z. This we want to prove. You choose any element in Z and can we produce pre-image here so that the image of Y, correct? So this we want. So you just choose any element from codomain of G, right? G is onto means what? That is what we want to prove. The range of G is whole codomain Z. This we want to prove. That is what we need to prove. G of y, which is G of y belongs to y. If you look at all the images, that will cover entire Z. The meaning is same. All these statements say the same thing. Is it correct? Right? Yes, claim is clear now.
Yes, sir.
How to initiate the process? We understand what is our aim, what is our target. So, how to initiate the process?
So we can say that since g of f is onto
See, what is aim? What is a claim? Ki given if you choose any element from Z, can you produce pre-image in G? Pre-image in Y. That is a claim. That means how to start the process. If somebody asks you prove that G is onto, how will you start? How will you prove that? How will you ensure that G is onto? What will you ask? Somebody says that he prove that G is onto. What will you ask? You will ask that he give me any element of Z. I will produce pre-image in Y. Is it logically clear? Yes. So logically, what we want to do, ki you will some if you somebody asks you to prove that G is onto, what you will say? You will say that ki give me element of Z, I will produce pre-image in Y. This is a process, right? So logically, what how to start? Your process starts with element in Z. You will just close your eyes or somebody gives you some element from Z. What you will do? You will try to search element in Y. If you are successful, then you will declare that key, okay, if you give me any element from Z, I can produce pre-image in Y. Correct? Do you understand? And this is our function G. Can you produce pre-image for every element here? So how to start the process? Logically, see, there is a lots of confusion. If you want to prove that G is onto, logically, how to start the process? Without taking element in Z, you cannot produce pre-image. So how process starts? So let Z belongs to Z, right? Choose any element from Z and now initiate the process of pre-image in Y. Is it clear? Is it clear?
Yes, sir.
Right. So Z belongs to Z and we want
Sir,
now Y in Y.
sir,
But
please scroll up.
now, so we have Z from Z. Since what is our assumption? What is our assumption here? G composite F is onto. This is our assumption, right? And what is a composite function? So composite function is from X to Z. And this function, so G composite F is onto and Z is in codomain of, so G composite is from X to Z and the element which we have chosen is in codomain of G composite F and G composite F is onto. So what I should say there? Since G composite F from X to Z is onto, what should I say further? Do you understand? X y, z, x, y, z, and G composite F. So G composite F is onto, and I have selected element from the codomain of G composite F, and G composite F is onto. So what should be my next sentence? What is my next sentence?
G of f of x equals to x.
What is X? What is X? See, you should see, whatever arguments you are making, you should make a habit of making clear and clean arguments. Right? If you want to learn mathematics, you have to be very careful. G composite F. What is the domain of G composite F? First tell me what is the domain of G composite F? X.
X.
What is codomain? What is codomain of G composite F?
Z.
Z.
Sir, you are muted. Sir, you are muted.
So G composite F is onto for any element in codomain of G. Can you produce preimage in X?
Yes.
Yes. So G composite F is onto, and we have selected some element from Z. So for Z belongs to Z, there exists X in X such that G composite F of X is equal to Z. G composite F is onto, so if you select element in Z, certainly there is a preimage under G composite F which is in X, right? But what is our main interest? Our main interest is to produce a preimage of Z in Y. This is our main interest. But anyway, can you understand what should be the process now? So I have produced preimage of Z in X. I have produced preimage of Z in X under G composite F. Now what is the right candidate for Y here? What is the right candidate for Y which we are trying to find?
F of x equals to y.
Right, very good. So we started with Z, but in that process, since G composite F is onto, we found X in X. So we found now X. Now apply F on X and look at F of X. Is it the right candidate for Y in Y? Then Y is equal to, then Y is equal to Fx. Is it in Y? Is the required preimage of Z in Y under G. Is it the required preimage?
Yes, sir.
Because
Yes, sir.
because if you apply G on Y, does it give us Z? Does it give us Z? If I apply G, that means G of Fx. if I apply, because if I apply G on this element Y, does it gives us Z? So G, which is G of F of X. But what is G of F? G composite F of X is already known that it is
Z.
Z, and
Z.
therefore this is the right candidate. Therefore, the preimage of Z under G is Y, which is Fx. And therefore, what is the process? If you start with Z, go back in X under G composite F and apply F on X, we'll get the right preimage of Z in Y. This is a process actually, so you should understand this process. Okay, how to produce preimage in Y, right? It is very difficult to see the preimage directly in Y. So you have to go to X and then from go X to Y. This is a actual, right. So is it clear? Clear? Is proof clear?
Yes. Yes, sir.
So give an examples of functions f g from Z to Z such that, now you find such functions from integers to integers such that G is not 1 1, so G composite F is 1 1, but G is not 1 1. Second, G is onto, but F is not on. So here you try to search such examples. That means F is from Z to Z and G is from Z to Z, integers to integer. Right, so you can think about such functions and try to find out such functions. Correct. So, but here if G composite F is 1 1, then F is 1 1, and if G composite F is onto also, then G is onto. Right. Now question I would like to ask, if G composite F is 1 1 and onto. So if G composite F is 1 1 and onto, then what happens? Can we say that? Can we say that F is bijection or G is bijection? Can we say this?
No.
Yes.
What is your answer? Yes or no?
No.
No. Right. Because if G composite F is 1 is 1 1. And more, or if G composite F is onto, then G is onto. That means if G composite F is 1 1 and onto biject, then certainly F is 1 1 and G is onto, but F may not be onto or G may not be 1 1. So from this we cannot conclude that F and G are onto. Right. But uh, if you have another situation like this, so if f is a function from set A to A such that f composite f. Now what can you say about f composite f? It is, what is the domain of f composite f?
A.
A. And what is codomain?
A.
A. A.
F. And I am again applying f, right? And therefore what is f composite f? F composite f is function from A to A. Is bijective. Then what happens? By previous statements, what can you say about this? Just go to the previous statement. If G composite F is 1 1, so when I say F composite F is bijection, F composite F is bijection means what?
If composite F is
F,
1 and F 2.
F is 1 1 and F composite F is 2. Right. When I say F composite F is bijective means F composite F is 1 1 and F composite F is on 2. But F composite F is 1 1 means what?
F is on 1.
F is 1 1. Right. When G composite F is 1 1, then the second F is 1 1. And if G composite F is on 2, then first function in the composition is on 2. So here for F and G are same. Right. So can I say that F is 1 1 and on 2?
Yes.
Can I say that F is just apply results? Then F is bijection. And why? This is a proof. Previous theorem, F composite F is bijective. That means F composite F is 1 1 and F of composite F is on 2. But we know that by previous two statements, F composite F is 1 1 means the second function which is F is 1 1 and F composite F is on 2. So first function which is F again on 2. So F is 1 1 as well as on 2. So F is bijection. Just immediate from previous statements. But in general, if F and G are not same, then not true, right? Correct?
So can we produce the different function from the same domain?
For which? What type of?
Means
Same.
if there is a composite function is bijection.
That
So
means if you want to find F from A to A and G from A to A. Right? So
yes, sir.
G composite F is bijection, but F is not bijection or G is not bijection. Right? This is your question.
Yes, sir.
Yeah, this is possible. That is what the exercise I gave you. What is this exercise? Z and Z, same A. Correct? It is possible that your function are not same. Then it is possible that composition is bijective, but functions are not bijective. Certainly, one of them is 1 1 and another is on 2. That is right, but may not be bijective. Correct? This is your question, right? And what is answer? Yes, there exist such functions. So find such functions. Is it clear?
Yes, sir.
Right. So you just sit down and take two sets, natural numbers, integers or real numbers, whatever you want, and try to produce such functions. That is an exercise because then you can understand the concepts. Right. Now we want to uh, get more stronger conditions uh, so that we can get some bijective function, or we can say whether the functions in composition are bijective or not. Okay, before going to this theorem, uh, what is the identity function on set A? What is identity function? You know definition of identity function,
fx equal to x
right? Fx is equal to x for all x in A,
for
right?
all x
Element
in
goes to C, right? So then F is called identity on A. So then F is called as an identity function on set A. We denote identity function on A by the notation identity on A. Right. So what is the meaning of identity? That means we denote such function by identity suffix A. Right. That is identity function on A, if we apply on any element of A, gives same element for every element in A. Correct? That means if we apply identity function on any element of set A, gives same element. So that's why it is called an identity function. Now we are in the position to state the theorem. So let f from x to y, from y to z be functions such that G composite f is from x to z is identity on x. Right, so what type of functions are this? The composition is identity function. Okay, I should make some changes in the statement. So what changes I should make? This is not a correct statement, because when you are saying identity, that means x goes to x. That means codomain of G composite F should be same. Correct? Is it clear? Okay, so what is the statement? What is the situation? I have a set x and I have a set y, and f is a function from x to y, and g is a function from y to x. And what is a composite now? What is a composite function? Composite function is from what?
X to X.
X to x, right? Because we start f takes element from x, gives element in y, and g takes element from y and gives element in x. So it is from x to x. Suppose this is identity. Then what is the conclusion? Then f and g is on 2, right? So if composition is identity function, then first function is 1 1 and second function is on 2. This is true every time. The statement is clear. Statement of theorem is clear.
Yes, sir.
Right. So let us try to prove this now. So what is given? What is given? F is from x to y, g is from y to x, and further what is given? G composite f is identity on x. That is G composite f of x is equal to x for every element in it, because domain of G composite f is x. Fine. What is our claim? What is our claim? We prove two claims. What is the first claim?
F is 1, 1 and G is on 2.
F is 1, 1. And second claim is on 2. Right. So let us try to prove first claim. First to prove F is 1, 1. So this is our first claim. Okay, how to initiate the process? That is, if you want to prove that some function is 1, 1, what we need to prove? Just recall the previous knowledge. What we need to prove that f is 1, 1. What we need to prove?
For every element of X, there is unique element in Y.
So distinct elements are mapped to distinct elements, right? What we need to prove? If x1 and x2 are two elements in domain not equal, then their images are also not equal. This is what the meaning of 1, 1. Am I right? If elements are distinct in domain of f, then their images are also distinct. F of x1 and f of x2 in the codomain. This is what we want. Alternate. This is equivalent to saying that if images of two elements are same, then the pre-images are also same. This is one and same. Is it clear?
Yes, sir.
Right. So what is our claim? F is 1, 1 means that is for x1 and x2 in x, f of x1 is equal to f of x2 implies x1 is equal to x2. This is we want to prove. We want to prove that f is 1, 1 means we want to prove this. So how to prove this? So start the process. We understand what we want to prove. First of all, try to understand what we want to prove, and then how to prove the next part. So initiate the process now. So suppose for x1 and x2 in domain of f, f of x1 is equal to f of x2. What we want to get now? What we expect? What we expect? x1 is
X1
equal to
equals to X1 X2.
Right. This is what we expect, but we have not proved it. Expect that x1 is equal to x2. Okay. Suppose x1 and x2 are two elements such that their images are same. Then we want to prove that pre-images are also the same. That means x1 is equal to x2. Okay, but x1 and x2, where are these two elements? Where are fx1 and fx2? Where are these two elements? fx1.
Y.
Why?
In Y.
Can I apply? Can I apply G? Right? If x1 and fx2 are two elements and they are same actually, same elements. If I apply G, then can I say that fx1 is same as G of fx2? Can I say this? Yes. Correct. Because fx1 and fx2 are the same elements from domain of G, and if I apply G, the result is same. That means G of fx1 is same as G of fx2, but this is same as G of fx1, that which is same as G composite f of x2. What should I say then? What is our assumption? What is our assumption?
G of x is one identity.
G composite f of x is equal to x for every element, and therefore what is G composite f of x1? Is it x1?
Yes.
X1
And
equals
what
to
is
X.
G composite f? X1 is equal to x2. Hence, we started with what? Fx1 is equal to fx2, where we reach x1 is equal to x2. Hence, f of x1 is equal to f of x2 implies x1 is equal to x2. Therefore, f is 1, 1. Right? If composite is identity, then the first function is 1, 1. Now, second claim. What is second claim? Is second claim. Correct? Yes. That means what we should prove? This is our function g. So that is to prove. What we need to prove here? G is onto means what? Yes. G is what is the domain of G?
Y.
Y.
Y,
Ah, and what is the codomain of G?
X.
X.
X. And we want to prove that G is onto means what?
For each Y in Y, there exists X in X.
No, what is the codomain of G?
For every x belongs to x, there exists y belongs to y.
G is from Y to X. And if you want to prove that G is onto means for every element X in X, can we produce pre-image in Y? Is it clear? Correct?
Yes, sir.
Right. Is it clear? Any confusion? There should not be confusion, because what is the meaning of onto? For every element in codomain of G, can you produce pre-image in domain? To prove for any X in X, there exists Y in Y such that G of Y is equal to X. This is our aim. Is it clear now? Okay, so
Yes,
how to get this? So how to achieve this? So how to start the process? We understand what is the aim. How to start the process? Let how to right where in process initiates. Suppose somebody gives you element from codomain of G, then your work job starts. Keep produce element in domain, which is a pre-image. So let X belongs to X. What we want? Y in Y, such that G of Y is equal to X. So this we want. I am writing this same thing again and again because you need to understand there is a confusion. What exactly we want to do logically, what we are doing, right? So let x in x. We want now y. So somebody gives you x, and what is in my mind? I want to produce y now. And how to produce y? Will it be possible? Let x in x. Can I produce y in which is whose image under G is x? How to produce? And what is the right candidate? What is the right choice for y here? What is the right choice for y? So what is in given x? X is known now. X is given. Can I apply f to x? Can I apply f to x?
Yes.
Yes. Suppose I apply. So if if I apply f on x to this element, if y is equal to fx, which is element of y, then what is g of y? Is it the right candidate? So x is given. Now I will apply f. I will get y, right? So I will apply x, f on x. I will get y. And is it the right candidate which we wanted to produce? We wanted to produce y. Is it the right candidate which we wanted to produce?
Yes.
Then what? This is the required pre-image of x, pre-image of x under G. Because why it is a required pre-image? Because if you apply G on y, can it produces x? Right? How to believe that this is a correct required y, which is a required pre-image? Do you understand? We started with x here and we wanted to produce y. But what we did, we started with x and apply f. We found some element here and that element is actually the required pre-image. Right? We wanted to produce some pre-image here. But we apply just f and we found some y and that is the required. So because why this y is the required preimage? If you apply g on y, then what is this? G of fx, because y is fx. This is g composite f of x. But what is g composite f of x? What is g composite f of x?
X.
X. And therefore now this verifies that g is y is the required preimage, correct? Therefore y is equal to f of x is a preimage of x under G, because if you apply G on Y, I will get X. Therefore, this is correct. So the proof is clear. Is proof clear? Hence, for every x in x, we can produce y in y. So G of y is equal to x. Therefore, G is 1, 2. So is this clear now? Is this clear? Yes. Any doubt?
No, yes, sir.
Now, suppose function from x to y, g is a function from y to x, like previous situation, such that g composite f is from what to what?
Y to Y.
No, g composite f. First we are applying f. That
X
means
to
what?
X.
X to x. Because when I say g composite f, that means we apply first f. But f can be applied on x only, so x. And then we apply g. But then where element will land? Because if we apply g, element will land in x. So codomain is x. Correct? Is identity. And what about f composite g? So f composite g is from what to what?
Y to Y.
Y to y is identity. Then what happens? Then what happens? So G composite F is identity, therefore by previous theorem, F is 1 1, G is on 2, and F composite G is identity, therefore again by previous theorem,
G is 1 1 and F is on.
right? G is 1 1 and F is on 2, right? Because no matter which set is X and which set is Y, doesn't matter in general situation. So if G composite F is identity, then first function is 1 1 and second is on 2. Similarly, if F G is identity, then G is 1 1 and F is on 2. And so therefore, what is the final conclusion? If G composite F and F composite G both are identity, then
F and G both are bijective.
right, F and G are both bijective. Right, so this is a conclusion from previous theorem. Now exercise find functions f from x to y and g from y to x. So G composite f is identity, but if G composite f is identity and f is not onto, G is not 1 1. If G composite f is identity, certainly f is 1 1 and G is on 2, but f may not be on 1 2 and G may not be 1 1. Now you find such function, G is not 1 1 and f is not on 2. You just have to search such functions from x to y and y to x. Right, so proofs clear. Any doubt in the proof?